Hello everyone, I'm Amaz Ali and today I'll be presenting my findings from Lab 4 which explores magnetic braking using Faraday's law. This lab has been fascinating and let's dive deep into it. In this lab, I delved deep into the electromagnetic interactions by observing and measuring the fall of a magnet through an aluminum foil tube. My main objectives were to understand Faraday's law in action, collect detailed experimental data, create a comprehensive computational model, and compare the two approaches. After numerous trials, I found that in my experiment, the magnet took an average of 1.55 seconds to fall through the tube. Interestingly, my computational model predicted a time of 1.21 seconds. This was a discrepancy of 0.34 seconds, and we need to understand why that there is a discrepancy. The two principles that were crucial for my experiment. First, Faraday's law of induction, which describes how changing magnetic fields induces electric motor force in the conductors. In my experiment, as the magnet fell, its changing position created a varying magnetic field. This induced a current in the aluminum tube, which is the essence of Faraday's law in action. The second principle is Biot-Savart's law, represented by the equation here. This law helped me to understand how the induced current in the tube generated their own magnetic field. This field helps interacted with the falling magnet, creating a force opposing its motion. Together, these laws explain the magnetic braking effects I observed. Now let's talk about the experiment. I used a straightforward but carefully designed setup. I dropped a bar magnet through an aluminum tube that was precisely 0.248 meters long, with a width of 0.0187 meters and an inner radius of 0.015 meters. These measures were crucial for both my experimental observations and computational observations. To ensure accuracy, I dropped the magnet multiple times, carefully timing each fall using a high-speed camera capable of capturing 240 frames per second. This allowed me to measure the fall time with a precision of 4 milliseconds. I repeated this process 5 times and calculated the averages. In addition to my hands-on experiments, I developed a detailed computational model to stimulate the process. My computational model used the same initial conditions as my real experiment. The code I wrote, which you can see in the snippet here, calculated several important factors. The magnetic field of the falling magnet at different positions using dipole approximation, the magnetic flux, each section of the tube as a magnetic field fell, the induced current in the tube, the resulting magnetic force on the falling magnet derived from Biot-Savart's law, the gravitational force on the magnet. By combining these calculations and using numerical integrations, I could determine the net force on the magnet at each point in the fall. From this, I predicted its acceleration and ultimately its fall time through the tube. Now let's analyze what I found about and explore the implications. As I mentioned earlier, my experimental time average was 1.55 seconds with a standard deviation of 0.03 across 5 trials. My computational model predicted 1.21 seconds. The difference of 0.34 seconds is significant and warrants further investigation. I believe it could be due to several factors. Possible miscalculation of the tube's electrical resistance. My model assumed a uniform resistivity, but the real tube might have variations. Small errors in measuring the tube or magnet. Slight inaccuracies in the experimental timing. Simplifying assumptions in my model, such as ignoring air resistance and assuming a perfect dipole magnetic field. The model didn't account for any deformations of the tube as the magnetic field passed. So now for the what if questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The magnet would fall down the tube more slowly. The induced current in the tube would become larger. A larger induced current would cause the magnetic field and magnetic force on the magnet to also be larger. What if the holes or slots were cut into the tube? How would this affect the rings current in your model? Holes or slots in the tube would disrupt the induced current in the tube. Disruption in the induced current would make the magnetic field lower. A lower magnetic field would cause a magnet to fall down the tube faster. In conclusion, this lab has given me a deeper appreciation for the complexity of electromagnetics. Thank you for listening. Goodbye.